Okay, a couple of questions now, a little more specific. I've kind of alluded to them already, but will we ever arrive at a previously constructed point? Now this means if we start from some arc that's an irrational multiple of the circumference and mark off multiples of that arc. We're not actually marking them off, but if we consider that the multiples of this arc could actually be constructed. So we construct multiples of the arc around the circle indicated by the white lines, and then we continue around the circle and we get to the orange mark, and we have a series of orange marks around here at intervals equal to this arc, and we get to here, and then we go one arc distance and we get to the yellow arc. We follow around the circle again, marking off equal arcs, and we end up here, and then another arc is equal to the, gets us to the blue arc, and so forth, and we continue this. Okay. Now eventually it's obvious that these marks are going to keep marching back this way until we get to the point where we have a series of marks from here to here. Now those marks will be equally spaced, here, 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 all the way down to the one before we get to this mark. But could this last mark here be equally spaced? Well, could the next mark after the one just before this point be equally spaced with the others between here and here? So, in other words, could we possibly land on this point? And if not, is it possible that as we continue filling this figure in, because after we get points filled up to this one, we're going to start filling points in between if we haven't landed on a mark, and you can think about how that would work. Will we ever land on one of the points that we've previously constructed, or that has theoretically been previously constructed? Then, another question. Given a point and a small number, no matter how small, will we ever arrive that close to our point? Now, that's a very vague statement, and I've made it a little more rigorous here, but let's see what we mean. Well, let's see what this feels like, okay? So here's a point, and if that point is randomly selected, then we're not going to land on it, at least in our first round, okay? So here's a point, some point, any old point, and then a small number. No matter how small, so we ever arrive that close to our point. What do we mean by this? This means if we keep marking points around here and keep going and keep going and keep going, and we get a small interval around this point, a small interval of closeness, okay? We're this close to the point within this interval here gets us to a certain amount of closeness, okay? The question then is equivalent to saying, is there any little interval of this circle in which we will never find one of the points, no matter how long we keep constructing? Okay? Is there any excluded interval? And I'll put it like this. This backward E means there exists, and a backward E with a question mark, it's a little, taking a little liberty with the notation, means does there exist? And I'm going to call this an excluded interval. Or, given any little interval along the arc, any little interval of arc, is it inevitable that this process will bring us to a point in that interval? And that's actually a pretty challenging proof, pretty challenging thing to think about. So you should get the question in your head. I don't know that you'll come up with a proof. You'd have to be, if you're at the stage at which I'm aiming these questions, it's a question that you can think about, but you've never been exposed to the kind of thinking, or unlikely to have been exposed to the kind of thinking that would allow you to answer the question. Now, you might be, 1 in a million smart, or 1 in 10,000, I don't know what it would take, and you'd be able to figure it out by thinking about it. So, don't hesitate to think about it every once in a while. Don't be discouraged from thinking about it, because the more you think about it, the better you understand certain things. Okay, well, the more rigorous statement of this, is there any pair x epsilon, that little Greek letter is epsilon, where x is between 0 and 1, and epsilon is considered very small. Okay? Now, x is going to be what multiple of the circumference we've gone through. Now, we're going to land somewhere on this circle, so we might as well say, well, x is between 0 and 1, meaning that we are between 0 and 1 arc length. So that means we could be anywhere on the circle, because x is going to be the multiple of our circumference. And epsilon is also going to be a multiple of our circumference, very small multiple. And the question then is there some pair x and epsilon for which none of our points lie between x minus epsilon and x plus epsilon times the circumference? And it's worthwhile to think about that for a while. I mean, if you think about it for 5-10 minutes and don't get anywhere with it, think about it for 3 minutes. Come back, a few days later, see if anything is assembled in your subconscious. Every time you think about it, it's likely to become clearer, but you might get to the point where there's an impasse and nothing ever becomes clear. Then here's another question, okay? What if this angle theta is a rational number? Okay? I don't mean that you're doing a rational multiple of the circumference, because I can tell you that if you do a rational multiple of the circumference, if your arc is a rational multiple of the circumference, then whatever the denominator of that rational number is, if you go around the arc that many times, you are going to end up at the starting point. And then you're just going to continue repeating points. You might prove that to yourself. That one's not too difficult to prove, but you got to have a pretty good understanding of rational and irrational numbers and what it really means for a number to be rational. It's still a fairly sophisticated thing to be able to really nail down, but not so sophisticated that it's not reasonably feasible. But I'm saying the angle is a rational number, the angle. And if the angle is just a number with no units, and that's implicit in what I say here, I said just a number. I didn't say a number of degrees. If it was a number of degrees, then you would eventually come back to your starting point and begin repeating points again, because there is a whole number of degrees around the thing, and a rational number of degrees would be a rational multiple of the circumference. And it might not be making any sense to you, but it's worth thinking about anyway. Okay, so if the angle theta is a rational number, meaning this very important point, a numerical angle with no units, and there are no units because I didn't say anything about units, is automatically in radians. So when I say a rational number angle, I mean a rational number of radians. Okay? And the rational number might be less than 1 radian, might be more than 1 radian. You know, it could be 1/2 radian. Okay, there's a rational number of radians. could be 3.5 radians. There's a rational number of radians. Okay, so those are questions, again, pretty challenging questions that use the concept of rational and irrational numbers. It require a good understanding of rational and irrational numbers. And these are non-trivial questions. These are fairly deep mathematical questions.